Alright, so today we're going to introduce a new concept called the Vesper theory, which stands for valence shell electron pair repulsion theory. We're actually going to do this in two parts. So this will be part one, which basically includes molecules that have coordination numbers of 2, 3, or 4. Alright, so Vesper, which obviously that's the way it's pronounced, is basically a theory that's used to determine the three-dimensional shapes of a molecule. Everything that we've been doing in class so far has been two-dimensional on pieces of paper and all that kind of stuff. So we're going to start looking at the three-dimensional shapes of these molecules, because as we all know, nothing exists in two-dimensional space. Alright, so the concept behind this theory is that all of these electron pairs, which as we all know have negative charges, try to get as far away from each other as possible. So imagine you and 8 or 7 of your closest enemies all in one room. Okay, and you would try to get as far away from each other as possible so that the greatest distance between every single one of you is achieved. And that's basically what the Vesper theory is all about. Okay, so the shape of the molecule will actually determine the properties of that molecule. So when you guys were in Biology 1 and you were talking about proteins and how their structure determines their function, it's a very similar thing for these smaller molecules that we're talking about in chemistry. So, to determine the shape of the molecule, the first thing we're going to have to do is draw a correct Lewis structure. Okay, and that's why we spent so much time working on Lewis structures, is you absolutely have to have a correct Lewis structure in order to get the correct three-dimensional shape. Alright, so after that, you're going to count how many electron pairs are around the central atom. We're going to call them groups or things, or because we can't really find anything better to call them. Alright, so you're going to decide how many of those electron pairs around that central atom are bonded and how many of them are the lone pairs. Alright, and then we'll use a Vesper chart, which you have in your survival guide, in order to determine the shape of the molecule. Here's kind of what the chart looks like. This is part of it, and this is the part that we're going to be using today. So you can see that these are the coordination numbers 2, 3, and 4, number of groups 2, 3, and 4, and you can actually find this in your survival guide.
Alright, when we're taking a look at the electron pairs, the thing you need to know is what do you count as a group around the central atom? When we look at the central atom, when you see a lone pair, which is represented as 2 dots, or you see a single bond, which is just 1 line, a double bond, which is 2 lines, or a triple bond, which is 3 lines, or 6 shared electrons between the atoms, they all count as the same thing. So what you're going to do is when you see a lone pair, single bond, double bond, triple bond, we are going to circle all of them because they all count here as being the same. We count those as groups. And the ones that have a bond in them are going to be considered the bonding groups, and the lone pair is considered the lone pair group.
Alright, so we're going to do some examples just to kind of familiarize ourselves with how to determine these three-dimensional shapes. So we're going to start with coordination 2, or 2 groups around the central atom. Okay, so our first example will be CO2. So remember, we're going to need to draw a correct Lewis structure, and that will actually look like this, with 2 oxygens double bonded to the carbon. Okay, so now what we're going to do is we need to determine the number of groups around the central atom. So I'm going to add in my valence electrons here to complete my octets. Okay, so we want to circle the groups around the central atom. Alright, so you can see right here this double bond, as we talked about before, was 1 group, and this double bond over here would be another group. And as you can see, there's nothing on top of the carbon, nothing below the carbon, so the number of groups on the central atom is 2. Alright, so now out of those 2 groups, how many of them are bonds? And as you can easily see, the number of bonds is 2. How many of those are lone pairs? Obviously 0. Okay, so in this case, and in all cases, you need to make sure that the number of lone pairs and the number of bonds add up to your total groups around the central atom. Alright, so if we go to our Vesper chart, we can see here that we have the number of bonds being 2, so we're going to stay on this line right here. Number of lone pairs, 0. Alright, so that's what we're looking for, and you can see the shape is linear. And you can see here's the example that we just used. All right, so if we go back, we can actually take a look at what this would look like in three-dimensional space. All right, and we call that linear. Okay, so don't say line ear because that's just weird. So if you're one of those people that says line ear, stop it. Okay, don't say line ear, it's linear. All right, so do not say line ear.
Hey, stop it. Stop it.
All right, Peter says stop it. Mr. Kleinschmidt says stop it. Mr. Herzog says stop it. So you better not say line ear. That's ridiculous. All right, so let's take a look at now something with three groups around the central atom, or what we call the coordination number 3. So here we have CH2O. So we'll draw the correct Lewis structure here. Carbon is going to be the central atom with hydrogen, and a double bonded oxygen. All right, so there's our correct Lewis structure. So let's take a look at the groups here. Now remember, circle those groups. Okay, so we've got a single bond here. That's a group. Single bond here. That's a group. Double bond here. That's a group. So the total number of groups around the central atom is 3. Now in this case, how many of those are bonds? Very easy to see, all 3 of them. How many are lone pairs? 0. So we go to our Vesper chart to find the shape. All right, so we're total number of groups right here, 3. All right, and we're actually going to be using number of bonds 3 and number of lone pairs 0. Okay, because that's what we just wrote down on the previous slide. If we follow that all the way over, that's what we have. The shape that we have is trigonal planar. You can see that we use the same example there. So we'll go back to our slide before. We'll call that trigonal planar. Some of you are going to want to say trigonal, and that's just weird. Don't say that. All right, and here's what that three-dimensional shape looks like. All right, so you can see it's all on one plane. It's got kind of 3 sides, so it kind of looks like a triangle, so we call it trigonal planar.
And if you draw this one, it just looks like a Mercedes-Benz emblem.
Yeah. Or, yeah.
Mercedes.
Okay. All right, so let's take a look at another example.
It's like it's not Volvo.
It's not Volvo. Don't drive Kias. SO2. So S is going to be the central atom. We'll have a double bond to an O, a single bond to an O, lone pair on sulfur, lone pairs on oxygen to complete our octets. All right, so let's check out the number of groups here. So here's a group right here, the double bond. Here's another group here, the single bond. And what most students really miss is right here. This is a third group, that lone pair.
Yeah, don't circle each lone pair, or don't circle each electron and say that's a pair, or that's a group. Make sure you circle them together.
All right, so we got our lone pair there. All right, so the number of total groups, the number of circles that we've made is 3. And out of those 3 lone pairs, how many of them are bonds? In this case, 2. Number of lone pairs, 1. Should check my work. I go 1 plus 2 equals 3, so I'm good to go. We go look at our chart. Okay, so we're still right here in group 3, but instead of being up here, we're down here now, where this is the number of bonds is 2 and the number of lone pairs is 1. And that three-dimensional shape is called bent. All right, so let's go back and we'll write the shape as bent, and I'll kind of drag that picture in here, show you what it looks like. So there's the bent shape. So a lot of you have been asking me and Mr. Herzog why we draw some of our Lewis structures the way we do, and the reason we do that is because we kind of already know the three-dimensional shape that those molecules take. All right, another example that we'll see a little bit later is water. Okay, we've all become used to drawing the Lewis structure of water as bent, and the reason is because the shape of water in three-dimensional space is also bent. Okay,
And just remember that the electrons are trying to get as far away as possible, and they're going to adopt these shapes in order to do that.
now we're going to move on to 4 groups, or coordination number 4. Our first example is CH4, and some of you have heard me talk about that in class. That is methane. That's what comes out of our little spigots here in the classroom. So carbon's the central atom. Yeah, spigot, cool word. All right, 4 hydrogens surrounding it. All right, so let's get our number of groups here. So we'll circle up our groups. 1, 2, 3, 4. So 4 groups around the central atom. 4 of them are bonds. 0 are lone pairs. We can take a look at our chart. So we're right here on 4. Number of bonds 4, number of lone pairs 0, and this shape is tetrahedral. All right, so we'll write tetrahedral is the shape. I'll kind of drag that in here so you can see it. Yeah, so it looks pretty cool. All right, and if I'm really bad at this, my organic professor tried to teach me how to draw this in 3-dimensional space. Kind of do this thing, and then it kind of looks like this, and this, and this. Anyway, that's
nice. Oh, those are supposed to be H's.
Whatever, Herzog. See, those are H's.
Oh, those are nice H's.
Those are great H's. Anyway, I'm rambling, so let's move on to another example. All right, NH3. And we know this to be ammonia, so this will have a lone pair here, and 3 H's bonded to the central atom, and I drew in red, so we'll get black. All right, so we'll circle our groups. 1, 2, 3, 4. So number of group is 4, number of bonds 3, number of lone pairs 1. Go to our chart. Okay, that's going to be right here. So that is trigonal pyramidal. That's a fun word to say.
Say pyramidal.
Trigonal pyramidal. Mr. Herzog says pyramidal because
That's how we talk in Chicago.
he's from Chicago, which, you know, they're weird people up there. So there's our trigonal pyramidal right there. You can see the lone pair.
Looks like a pyramid shape.
Yep. So you can see kind of the pyramid.
Triangle
Not as good as the Egyptians, but that's all right. The Egyptians were pretty awesome at pyramids, I guess. All right. So here is our last example. All right. This is water, H2O. So O, H, H. Lone pair, lone pair. That's a bad lone
That's a
pair.
very bad lone pair.
That's a little bit better, I guess. Don't judge me. I know you're sitting at home judging me right now. Stop it. Alright, so here's our groups. So you can see we have 4 groups around the central atom, 2 of them being bonds, 2 of them being lone pairs. And if you check our chart, it's right down here, 2 and 2, and that is the bent shape. Alright, so we'll go back in here, we'll write bent, and there's kind of what it looks like. Alright, so that's basically it. So remember, this chart is in your chemistry survival guide, and we'll be doing some examples on part 1 in class at some point, probably tomorrow. So be prepared. And if you have any questions, let us know at the beginning of class. And be on the lookout for part 2, which should be coming your way tomorrow.
Bean.